Hi everyone, welcome to the series on Databricks. This is the first lecture where we're going to cover the basics of data lakehouse architecture and its evolution. Um, so in this video, we're going to talk about the evolution of data architectures and the brief history of relation databases. Along with that, we'll also talk about data warehouses and the next step is data lakehouse, or particularly data lakes and Delta Lake, which is basically a brand name for data lakehouse, right? We'll also talk about medallion architecture and then finally the Delta ecosystem, right? So the Delta Lake ecosystem. This is a very interesting series, and we'll have multiple videos on the same. So stay tuned. Okay, so let's start with the evolution of data architectures. Obviously, we all know data warehouses are, very important because basically data warehouses essentially run the world, right? So if every time you go and swipe your card, the bank deducts the money from your card and then makes a payment to the merchant. In the back end, the whole thing is basically managed by a database, right? Similarly, when you shop online or book tickets online, everything essentially is data, and the data resides in a database. Now, there are different types of databases and different applications based on those different types of databases. We'll talk about that briefly, but essentially, the idea is that we are going to cover data warehouses a little bit more and then move on to the next version, which is basically data lake. When we say data lake, we are talking about big data, right? You all must have heard of Hadoop and the ecosystem, wherein there is massive amount of data that sits in object stores, and then it is processed using Hadoop and other technologies, right? The next bit of the evolution is what is called as data lakehouse, which is an interesting evolution in the sense that it has some of the best features of both data lake and data warehouse. So without further ado, let's get started. Okay. History of relationship databases is pretty old. As you can see, 1970s is when we seen the concept of relational databases, where there is emphasis on logical structure relations between the data. So, for example, when you go and put your card in the ATM, the ATM comes back and shows you this is the balance, right? So there's a mapping between your card number and the account balance and so on and so forth. There's a whole bunch of obviously data processing that happens in the background, but that relationship between your card number and your identity and the bank balance is basically a relation, right? And that's the idea. That's a fundamental design there. Now, obviously, IBM is the pioneer in this, and they've introduced this concept in the 70s. Ever since then, there's been an explosion in the uses of databases, as we all know. Okay. Like I explained previously, simple example of relationship database is basically where you have let's say a customer and then transactions and orders and all of that. So you have a separate table for orders, you have a table for customers. When a customer requests some data, you join them and look for the customer ID and get the data, right? And the reason why you want to have two separate databases is basically you want to keep uh, the customer information in one database and the orders in the other database, what we call as fact and dimension. Um, Now, relationship databases have been obviously ruling the world ever since the 70s, right? So in the 80s and the 90s, we have all these different databases that have come up. The more popular ones are Oracle, right? Oracle is obviously a big player in this game, and they've come up with this concept of asset properties, which are very useful in the database world, right? Now, what the reason why the relationship database has been so successful is because they have these asset properties. At the same time, in the 2000s, right, with the explosion of internet and so-called JSON-like data or semi-structured data, the relationship databases have not been very helpful in handling those things, and that's why there has been evolution in that sense. It's not the relationship no database is no longer useful. They're absolutely useful. In fact, they run the core things of the world, like orders and bank balances and all that. But now we have this additional data, or what we call a semi-structured and unstructured data. We need a database modeling mechanism to handle that as well, right? That's the whole point, okay? Now, the limitations are, like I said, like we discussed, sorry, okay. So basically we can't handle the unstructured data or semi-structured data. Now, coming to the next version, which is basically your data warehouse. What we mean by warehouse, data warehouse is like a normal warehouse. You store a bunch of data here, okay? Uh, Data that is not directly used for day-to-day transaction processing. So here comes the concept of OLTP and online analytical processing, right? So transaction processing and analytical processing. So when we say transaction processing, we're talking about actual transactions that deal with customer data or something like that. Whereas analytical processing is more for understanding what is happening in the business and making reports and dashboards and presentations based on that, right? So we are more the next few series videos are all going to be on the analytical stuff, not much on the transaction stuff, because the transaction stuff is something that's not in the purview of data engineering per se, right? So we're talking about more of the analytical stuff. When we're talking about the analytical stuff, we have a thing like a data source, a staging area, and then we do a job like an ETL job, and then push the data from the ETL to wherever you want to store it. And you could make things like data marts, and then you can also make like a aggregated table, and then from there you can do visualizations and so on, right? That's the whole schema structure design for data warehousing. Now, the need for data warehouses has become apparent after the explosion of OLTP type databases like Oracle, right? Because you have all this data now, people want to understand the data, analyze the data, and see if there's any, they can make some sense out of it, and then improve the business viability and all that, right? So basically, in the 90s, there's been an explosion in that, right? So data warehousing, basically, 1990s and 2000, early 2000s. Okay, now, as you can see here, like we discussed previously, there are data source layer where data comes from, and then there's a staging layer, and then staging layer is the data gets dumped into. Then from there, you do what we call as ETL, extract, transform, and load, and then you have different stages there. So you take the raw data, put it in one place, and then do something on top of that, like for example, maybe clean it. That's the second step. And the third step would be build like, aggregated data. So you, from the data tables, you build things that you want, and then in a way you want, and then make queries faster and all that, right? So that sort of thing. And then basically aggregated data feeds into the actual stuff, like, maybe you want to build a visualization, or you want to build a report, or some analytics, something like that, right? That sort of thing. Okay. So like we discussed previously, ETL or extract transform load is essentially extracting data like what it says, and then you want to transform the data, and then you also want to load it into a particular place, whether it's data mart or a different table and so on and so forth. Okay, now basically a staging area is where you dump the data, right? You can get data from different data sources. It could be your RDBMS databases or SQL Server, or it could be flat files, or it could be some other sources like JSON, web data, or log files, etc., etc. So all of that data is coming from some different places, and you're taking the data, dumping into a staging area, and from then you're doing your ETL jobs. That's the idea here. Okay. Hey, okay. So as part of data warehouse content classification, we have different types of data, and each type of data has its own purpose and use case, right? So essentially, you have the raw data. So the raw data is, uh, something like a transaction data, or, some other data basically, which could be maintained. It's an original format, and which will essentially be used in ETL, right? Now, apart from the raw data, we also would have what is called as metadata, which is basically data about data. It'll set the context, so it'll give you details like the data description, column description, when was the last refresh like, etc., etc., so on and so forth, right? So all of these additional things, which is basically talking about data itself, is called metadata, and that has its own use case. Now, on on top of that, we also would have what is called a summary data, which basically helps in speeding up queries, essentially, right? It basically things like, let's say you have a partitions, 20 partitions or something, and then if you sort data by certain order, then you have a query that comes in, you have a summary statistic which says the range of data for this partition is, let's say, 50 to 100, and then you have a query which has a filter and it says I need only data which is greater than 200 or something like that. Then you don't have to go into that partition, right? So it saves up that additional scanning time. So basically, that's kind of like summary data. So these days, it's very common to have a lot of different summary data for each of the partitions. So it helps in speeding up queries and many other things, right? So essentially, that's the way data warehouses are set up, modern data warehouses. Now, as part of setting up these databases, you would have to do what is called as dimensional modeling. So essentially, dimensional modeling is about how do I set up my database, right? Okay. The idea is you have all this data coming in. How do I make sure that A, the data is easily accessible when you want to get it, and B, it's fast and accurate. These are the two ideas. Okay. Now, as part of dimension modeling, what we have are two key things, which are facts and dimensions. We're going to see that in the next slide as well, but basically fact is a fact, an actual event, right? And the dimension is something that kind of combines with the fact and gives you broader, more useful information, right? Something like, let's say there's a user, you have a user who's doing transactions. The actual transaction data is a fact because it's a factor for an event sort of thing. And then some data about users profile and other things that could be that doesn't change, right, as often. So that is like a dimension. Okay. So you combine the fact and the dimension, then you have basically a better picture or complete picture and that sort of thing. So as we can see in this picture, you have customer table, then there's a sale, then you could have different things like a channel, product, whatnot. So all of the other things could be dimensions, whereas the say actual transaction is basically a fact. Okay. Typically, what happens is a fact table would have a lot of data, right? Because uh, a single customer could do multiple transactions across their lifetime. And if you're capturing things like click, stream, activity, or something like that, that's literally millions of data points just for one user. So that could become a fact there. It's like a transaction. That typically is pretty large. And the reason why we need to identify this distinction between the scale of fact and dimension is that when you are optimizing certain queries, you could do broadcast join, which is a form of transaction processing in Spark that actually speeds up queries. But the condition for that is that when you're combining two tables, when you're joining two tables, right? One table has to be very small so that you can do broadcast. Basically, that's called broadcast join, which probably we'll discuss in a separate series called on Spark or something. Discuss that later. But that is very important to know. Okay, so let's just discuss the benefits of data warehouses. So data warehouses, like we discussed previously, centralized data source for comprehensive analytics. That's the main use case. You can also do historical data analysis, and you can support diverse analytical tools and reporting capabilities, etc., etc. So traditionally, they have been, sort of like the workhorse of, a company's analytical divisions and all that. So it's been there for quite some time now. We also discussed the benefits. Now we also discussed the cons of them. Now let's go to the next one. right? So like we discussed, basically this is a pictorial representation wherein what we are saying is you have all these data systems that feed in data to your data warehouse through ETL, right? And then the data sits in the data warehouse. From there, you do your reporting, analytics, data mining, data science, etc., etc. So that's the big high level picture. Okay, I guess we've already discussed the summary multiple times, so I'm just going to skip this. Now, let's get into data lakes, right? So what is a data lake? So basically, data lake is something where we don't do a lot of processing, right? So what we mean by that is we store the data in its raw format, in its native format, and we don't do any processing. The idea is you just dump the data into a data lake, right? And from there on, you would run a processing engine and then basically get build something in a data warehouse. This is what was going on for the last, before data lake houses came about. This is what was going on. So you had Hadoop data lakes, and then you had Informatica, ETL, data warehouses, etc., etc. So people used to combine them and then kind of get stuff going, right? But that was like a patchy thing, and it has its own pros and cons, I guess. But it's kind of like now we're moving to the next phase of things. But anyways, so idea is in a data lake you have all this data that sits, and then from that itself you could do your uh, processing, big data processing, and then build analytics, and you put the data in a separate data lake or a file system or something like that, right? And then every iteration you have something else. So you take the data, you store it in place A, do some iteration processing, then store it in B, and so on and so forth. So that's how data lakes typically work. Um, so the thing is more like one of the biggest pros of data lake is that they support wide variety of data formats, right? Whereas if you remember, data warehouses don't do that. Data warehouses typically only support structured data. What we mean by structured data is basically something like an Excel sheet or a CSV or whatever, data table and all that, right? Whereas the advantage of data lakes is that because they're object stores at the end of the day, they're able to store all these different types of data, whether it's structured, semi-structured, unstructured. So in that way, what happens is it's like your baseline storage. So it stores anything and everything, right? And from you, that's like one place where you can put anything, and then from that you build all your other layers of analytics and whatnot, right? And that's the main biggest advantage of data lake, in my opinion. The idea again is basically improving the accessibility for data and democratization, etc. Right? So we discussed this already. Um, okay, I guess we also discussed this quite a bit. Just quickly going through, uh, you know, high level they're similar, but the main difference is that we discussed, we don't enforce schema. We don't enforce strict schema on data lake, whereas data warehouse has a schema enforcement. Um, okay, okay. So the biggest difference, in my opinion, for data lakes is that uh, compared to data warehouses, this is a big one, which is basically storage and compute, right? Um, they are different. So what we mean by that is you could simply store a lot of data on data lakes and not do any computation. You don't have to increase your compute capacity, CPU, or anything like that. That's a big advantage because then you can have commodity hardware store your data, and then you can do analytical processing on demand. And that was the biggest selling point for data lakes. And from the 2010s, the big uh, push for Hadoop-based systems were primarily because of this, because you could store lots and lots of data very cheaply, and then compute that at, at like on demand whenever you want it, right? As long as data is reasonably structured and all that. But that is only possible because the storage and compute was separated, right? If they're combined, like in the case of data warehouses, if you want more storage, you have to get more compute, and the compute is typically very expensive compared to storage. So that was the problem that data lakes primarily solved, right? Um, okay. Now, some of the challenges of traditional data lakes are that is that because you're kind of dumping data without thinking ahead, right? It quickly becomes what we call a data swamp in the sense that there's a lot of data, but you're not able to use it effectively because you don't have the kind of like the schema enforcement or schema evolution and all of the other metadata related stuff that we discussed previously. All of that, if it's not done properly, or the data governance, if it's not done properly, like it happens in data warehouses, the data lakes lose some of their effectiveness. And that's the biggest challenge with traditional data lakes, right? Now, introducing data lakehouse again. So what we are saying is basically data lakehouse effectively solves the issues of their precursor, which is data warehouses and data lakes, right? So the advantage of data lakehouse in some aspect is that it enforces schema, but utilizing the underlying cheap hardware and then separating compute and storage. So it's like the best of both worlds in that sense. Uh, this concept is introduced to the world by Armbrust and Godsey. These are the guys who kind of invented the Databricks guys. These are the guys. Now, what they saw is clear uh, necessity for ACID compliant transactions, right? For data lakehouse. So the beauty of the data lakehouse is it has ACID compliance, which is kind of like the gold standard for computation analytics, right? So if you are able to comply with the ACID transactions, then what happens is transactions don't fail in the middle, and then there is atomicity. So if it either goes through or doesn't go through, all of those good things that we have through ACID transaction properties are there in data lake. So this is a big thing because until data lakehouses came about, it was a very complicated thing. You had this proprietary data warehouse solutions. They never tell you what is happening under the wraps, right? Because it's proprietary. So because it's proprietary, the costs are very high, and then you're locked into these vendors and all of that are the issue, right? So in my opinion, even if you're not able to, if it's not a big advantage for unstructured data, like for example videos or whatever, I think data lakehouse is a fantastic thing for structured data because you are able to get all these ACID properties at a throwaway cost just using commodity hardware. So in that sense, you can literally run massive machine learning algorithms and all of these other analytical things without burning the bank, right? So basically, with low cost, you're able to do that, and that's amazing, and that's why this is picking up like crazy. Okay, so again, the underlying of the whole thing, data lake house, there's a data lake, right, which stores structured, semi-structured, unstructured data, and then on top of that you have the metadata, and then you have indexing, then you have caching, and then you have the summary data. All of that there, all of that is created as you create uh, the tables in what we call as delta lake tables in the implementation, right? And then once all of that is created, then you can do your BI jobs, and then or you can connect it with Power BI and then do reporting or do machine learning, etc. Right? Okay, like we discussed again previously, the benefits are uh, it leverages the low cost cloud storage, and then it's detached from compute, so you're saving loads and loads of money there right away. And then because it complies with ACID properties, so it's a fantastic thing for transaction support.